two ordinary containers do not share a localhost. If a frontend dials 127.0.0.1 port 8080, it reaches only its own network stack, not the backend next door. Put both containers in one Kubernetes pod, and that same address works. So what exactly changed? Here is the behavior on a real Linux host. One container runs an HTTP server on loopback port 8080. A second, normally isolated container requests that same loopback address. The connection is refused, because localhost always means the network namespace of the calling process. The useful mental model starts below Kubernetes. A container is not a tiny virtual machine. It is one or more ordinary Linux processes launched with a configured file system view, selected namespaces, security settings, and cgroup membership. The kernel still schedules processes, the runtime assembles their boundaries. A Linux namespace wraps a kernel resource so member processes see their own isolated instance. For pods, 5 types matter most: network for interfaces and ports, PID for process IDs, MAN for mount points, IPC for shared memory mechanisms, and UTS for hostname and domain name. The network namespace is the key to the mystery. It contains the loopback interface, network devices, IP protocol stacks, routing tables, firewall rules, and socket port numbers. Two processes in different network namespaces can both bind port 8080 because those sockets live in different stacks. Docker exposes the underlying primitive directly. The second container can join the server container's network stack with network mode container. Nothing Kubernetes specific is involved. Once the client joins the namespace, the identical request to 127.0.0.1 port 8080 reaches the server and returns successfully. Now for the strongest proof. Linux exposes each process's namespace handles under proc, PID, NS. The server and joined client report the same network namespace and node. The isolated client reports a different one. Matching identifiers mean those processes are members of the same kernel namespace. Sharing the network stack also means sharing its port table. The first process binds port 8080 successfully. A second process in the same namespace cannot bind that address and port again, so Linux returns address already in use. Localhost convenience and port collisions are the same mechanism. Kubernetes adds orchestration around that primitive. The kubelet asks a CRI-compatible runtime to run pod sandbox. The runtime establishes a pod-level execution environment, creates the network namespace, and typically asks a CNI implementation to configure the pod network before application containers are started inside the sandbox. Uncommon Linux implementations, a tiny infra or pos container traditionally holds the shared namespaces alive, and application containers join them. But keep the abstraction honest, Kubernetes guarantees pod behavior through CRI, not one universal post-process design. A virtual machine runtime on your sandbox controller can implement the boundary differently. The user-facing pod spec is deliberately less mechanical. It names two containers that belong to one pod. There is no field saying share loopback. Pod networking already defines that behavior. The containers receive separate images and commands, while the runtime places both into the pod's network context. Both processes now see the same loopback device. When the backend binds 127.0.0.1 port 8080, that socket is registered in the pod shared network namespace. When the frontend connects to the same address, its request enters that same stack and finds the backend listener. Loopback is only part of the shared identity. Every container in the pod also sees the same pod IP, interfaces, routes, and network ports. From the network's point of view, the pod behaves like one logical host. Containers outside the pod address the pod IP, not an individual member's private IP. That design has a useful trade-off. Sidecars and tightly coupled services can use loopback without service discovery between them. But every member must coordinate port choices, and the listener exposed on the pod interface is reachable as part of the pod, regardless of which container started it. The dangerous shortcut is saying that containers in a pod share all namespaces. They do not. Network and IPC are pod scoped in the normal Linux model, and members see the pod hostname. Their file system views remain container-specific, and their PID namespaces are container-scoped unless process sharing is explicitly enabled. PID behavior makes that selectivity obvious. By default, each regular container gets its own process ID namespace, so process listings do not expose sibling containers. Set shareProcessNamespace to true, and the runtime gives the pod a shared process view, which enables cross-container inspection and signaling subject to permissions. files work differently again. Each container starts from the root file system supplied by its own image. A Kubernetes volume is a separate directory that the pod declares, and each container independently chooses where to mount it. Shared files come from that explicit mount, not from merging container root file systems. Two smaller details complete the picture. Pod containers can use standard operating system IPC such as system v semaphores or POSIX shared memory, because IPC is pod scoped in the Kubernetes Linux model. They also see the same configured pod hostname, reflecting the shared UTS context. Then there are C groups, which solve a different problem. A namespace changes what a process can see. A C group organizes processes hierarchically and controls or accounts for resources such as CPU and memory. Container systems use both, but calling C groups another isolation namespace hides the distinction that matters. Why keep a stable sandbox at all? Application containers restart. If this shared namespace were owned only by whichever application happened to start first, replacing that container could also destroy the pod's network identity. A sandbox starts first, remains while members come and go, and releases shared resources when the pod sandbox ends. Put it together and a pod becomes much less mysterious. It is Kubernetes scheduling and lifecycle unit for one or more containers, with a shared network identity, selected shared namespaces, independent container images and file system views, and volumes shared only where the specification mounts them. If you build a pod-like primitive in any orchestrator, the implementation questions become concrete. Which process or sandbox owns each namespace? Which containers join it? Which resources are pod scoped, and how long do they survive? Once those answers are explicit, the abstraction stops feeling Kubernetes specific. So when localhost suddenly works between two pod containers, no networking law was suspended. Kubernetes arranged for both processes to enter the same network namespace. They now share loopback, interfaces, routes, the pod IP, and the socket port table. The mystery is namespace membership. A pod is not a special kind of container. It is a group of containers with a carefully chosen set of shared Linux resources and one Kubernetes lifecycle boundary. Once you see the namespaces underneath, localhosts, sidecars, port collisions, and pod sandboxes stop looking like magic.